Hello, students. Today's topic is the types and applications of polymer orientation. In this lesson, we will learn about the types of polymer orientation, the applications of orientation, and the factors that affect orientation. In the application of polymer materials, the performance of materials and products can be improved by controlling different orientation methods. The types of orientation include: first, uniaxial orientation. When a polymer is mechanically stretched, the molecular chains align along the stretching direction. This results in increased strength and modulus in that direction. However, the performance perpendicular to the stretching direction may decrease. Second, biaxial orientation. The polymer is subjected to stretching stresses in two different directions. This causes the molecular chains to orient in two mutually perpendicular directions. This significantly improves the material's biaxial strength and stability. Third, flow orientation. When the polymer is in a molten state or solution and subjected to shear forces, the molecular chains tend to align along the flow direction. This orientation primarily occurs during processing, such as extrusion and injection molding. For oriented polymer materials, significant changes occur in their mechanical, optical, and thermal properties. For example, in mechanical properties, tensile strength and fatigue strength increase significantly along the orientation direction. However, in the direction perpendicular to the orientation, they decrease. Therefore, orientation can be controlled to improve certain properties of the product. The applications of polymer orientation are mainly in the following areas: production of synthetic fibers. Orientation can be used to produce high-performance synthetic fibers. Spinning involves extruding the melt through a spinneret, then using high-speed stretching to obtain highly oriented fibers. Stretching increases the degree of orientation of the fibers. Tensile strength is enhanced. However, in practice, if the orientation degree is too high, the molecular arrangement becomes too orderly, and the intermolecular interactions become too strong. The molecular elasticity decreases, and the fibers become stiff and brittle. To obtain fibers with both strength and elasticity, the molding process can be adjusted by utilizing the different speeds of molecular chain and segment orientation. A slower orientation process can be used to give the entire molecular chain good orientation to achieve high strength. Then, a faster orientation process can be used to partially deorient the segments, giving them elasticity. Second, application in film production. Stretch orientation can be used to produce films with the required performance. Currently, the widely used isotactic polypropylene strapping ropes are made from isotactic polypropylene films that are first stretched uniaxially and then torn. The uniaxial orientation generates an ordered arrangement. The strength is high, making them very strong. However, in the perpendicular direction, the arrangement is disordered, so the strength is low and they tear easily. For products such as film bases for movie films, audio and videotape bases, and other films, which require isotropy in the plane, they need to be produced by biaxial stretching. Due to biaxial orientation, the film does not have a weak direction. It can comprehensively improve strength and increase resistance. Moreover, because there is no anisotropy in the plane of the film, it does not undergo uneven shrinkage during storage. This is very important for film materials used in photographic film. It will not cause image distortion. Third, application of orientation in plastic blow molding. For plastic products with simple shapes, blow molding can be used to induce biaxial orientation of the polymer to improve strength. For example, transparent cockpit windows made from PMMA on fighter jets, or safety helmets made from PVC and ABS, where impact strength is improved after orientation. Fourth, applications of orientation in molding processes like injection molding and extrusion. Orientation can be controlled during extrusion, injection molding, and other processing methods to improve product performance. For injection molded products, if large performance discrepancies are undesirable, the occurrence of orientation should be minimized. Complete orientation is not achievable in polymer molding. Orientation degree can be controlled to manage material properties. This requires an understanding of the factors that affect orientation. The following factors affect polymer orientation. First, temperature. As temperature increases, the polymer's thermal motion accelerates, increasing the orientation speed. However, deorientation also increases. The final effective orientation of the polymer depends on the balance between these two processes. Second, stress and time. The greater the stress, and the longer the duration, the higher the degree of orientation in the product. Third, the influence of polymer chemical structure. If the polymer macromolecule has a simple structure, it is more flexible, and the average molecular weight is low, making orientation easier. Conversely, it is more difficult to orient. Fourth, the influence of additives. Low molecular substances added to the polymer, such as plasticizers and solvents, can lower the glass transition temperature of the polymer, shorten the relaxation time, reduce viscosity, and facilitate deformation. This makes orientation easier. However, the deorientation speed also increases. Additives with a very obvious directional shape, such as fibrous or needle-like fillers, make orientation easier. In summary, the types of polymer orientation include uniaxial, biaxial, and flow orientation. Orientation can be controlled to improve certain properties of products. High-performance fibers can be produced by orientation. Films with required properties can be produced using stretching orientation. Biaxial orientation in blow molding improves strength. Orientation during extrusion, injection molding, and other processes controls the product performance. Factors affecting polymer orientation include temperature, stress and time, polymer chemical structure, and additives.